Well, good morning. My name's Brian Haynes from the University of Sydney, and it's my pleasure this morning to introduce our plenary speaker. I should say in the start that this story goes back to 1980, when as a young researcher I received a package in the email. And the package contained a microfiche and some very complicated workings of the transport equations and chemical kinetics, and I didn't quite know what to do with it. It was called Chemkin, and it was a couple of years later before I actually finally worked out how to use Chemkin, and have been using it ever since. And I think one of the principal architects of the Chemkin package is here with us today and is to give our plenary lecture. It's Professor Bob Key from the Colorado School of Mines. And Bob is extremely well known, of course, for his work on Chemkin, but I think also what I like about Bob's work is the fact that he has been able to take his deep understanding of combustion and apply it to a range of other combustion-related problems. And I think that's a wonderful object lesson for the rest of us who work in this exciting field. Bob, of course, is the recipient of the Bernard Lewis Gold Medal to be delivered at the banquet tomorrow night. So without any further ado, I'd like to welcome Bob to the podium to deliver today's lecture.
Thank you. Well, thank you very much, Brian, and thanks, Peter and Assad, for this very kind invitation to share with you some of the things that we're doing. I want to, as I start, acknowledge two colleagues who have contributed greatly to this work over many years, my colleagues Janan Karakaya and Huayang Zhu, both of who are who are with us at this meeting today. So, as Brian just said, a lot of our work has its foundations in combustion, but we've looked for new things, many of which I'll share with you today, certainly not all. So the text of what I want to talk to today has to do with conversion, especially of natural gas, but methane, to more valuable chemicals. As you're all very well aware, technology such as fracking has fundamentally changed the energy landscape, certainly in the Western, in the US, but worldwide. So here's a picture of a well in Colorado, and the reason I show that is, one, it's close to home, but the other is gas is often stranded, meaning it's hard to move it from where it comes out of the well to where it can be used. And so converting that gas to something else, liquid for example, has great value, and that's part of what I want to talk about today. Oops. So there are many opportunities, gas to liquids technologies. In this talk, I'll first talk about syngas routes, which I think will be actually quite familiar to this audience, and then talk more about oxidative coupling and direct dehydrogenation, which may or may not be quite as familiar. And throughout the talk, I want to bring in the notions of process intensification, looking at how to scale from refinery scale or very large manufacturing towards distributed processes, such as might even be used at a wellhead. So, as I started thinking about this particular talk, I wanted to set it in the context of what do we as a combustion community, where are our foundations? What do we really know well? Actually very well compared to many other groups of engineers and scientists. And I've listed a few here that I think everyone will agree with. I'm simply showing actually a relatively old picture of a turbulent flame from Godfrey Mungel's group some years ago. But this community is really very comfortable with chemical complexity. That's not always the case in different communities. And not only chemical complexity, but fluid mechanical complexity, coupled heat and mass transfer, advanced diagnostics, modeling and simulation, and the ability to scale from fundamental research to practical application. I mean, these are foundational things that we're really very good at as a community. Now, as I look to opportunities and things that I'll talk about today, we need to build upon that foundation to extend, to do new things. So one is, what I'll talk today is mostly transforming fuels, not oxidizing them. They're still chemically complex, almost always operating on heterogeneous catalysis, but not always. Oftentimes, we're working at high pressure, low temperature, very non-ideal fluids, supercritical sorts of behaviors. And a place that I'm spending a lot of my own creative energies these days is in electrochemistry. I'll really very, very briefly touch on that in this talk, but quite an important topic in its own right. So here's the outline for the talk that I'll give today. I'm assuming we'll start with clean natural gas. What I really mean by that is methane. And there's a lot of technology to get from real natural gas to methane before we actually go into other processing. I'll review, and I think that is largely review for this group, a little bit about a syngas, which is the most traditional way to move from methane to other fuels is go through syngas. I'll talk a little bit about FischerTropsch in the context of process intensification. Actually, I won't say anything here about methanol, and then spend some time on oxidative coupling, as well as methane dehydroatomization, ultimately leading to chemical feedstocks that are input to further downstream processing. So let's start with syngas and reforming. So I want to call your attention or remind you of two things that are important. One is the heats of reaction, either endothermic, I mean strongly endothermic for typical reforming, or reasonably exothermic for partial oxidation, combinations that are autothermal. I mean, we're often thinking about how to manage the temperature in reforming processes. What is often less talked about is the need to produce certain hydrogen-CO ratios depending upon what your downstream process is. So for example, if you're going out to a FischerTropsch process, you need 2 hydrogens for every CO, but for example, if you want to make acetic acid, you need equal parts. And so attention both to the process temperature and the exo-endothermicity of the chemistry together with the product composition is actually quite important. So one way to conceptualize that in a simple picture is shown here in a so-called ternary diagram that's simply plotting the equilibrium reforming chemistry. But what I've shown here is a couple things that are important. One is this red line is the Koch line. So if we have a feed stream that's above this line, thermodynamically, the most likely thing to do is to make coke or to foul the catalyst. So usually we don't want to be there. The star here, actually I should put an asterisk on that because the plenary yesterday said we actually do want to be here. Anyway. The other thing that I've shown on here is iso lines of the hydrogen-CO ratio. So again, as I just said, depending upon what you want to do with the syngas, you're concerned about coking, you're concerned about controlling temperature, and controlling the hydrogen-CO ratio. Now, this picture it carries a lot of information, but it's at equilibrium. And as we well know, most processes are not equilibrated. We have kinetics to deal with. So here I'm showing what I've labeled to be a typical Deutschmann mechanism. Probably 80 to 90% of the catalytic chemistry that's used in this community finds its way back to roots in Karlsruhe in Olaf's group. And so there's great value in this elementary chemistry. I won't go into this in any detail here, but plainly this is more complex than a simple global reforming reaction. It has great value because it spans the space from reforming, dry reforming, partial oxidation. It's all captured in these reaction mechanisms. As shown here, this is on nickel. I will later in this talk about much more complicated catalysts and some of the things that we're active in today. And I'll also talk briefly at least about when the page is blank, how does one actually produce these mechanisms? And it's difficult. Also call attention to a place where we need a lot of help is in microscopic reversibility, right? So in gas phase chemistry, we almost just take it as given that we've got microscopically reversible reaction mechanisms. But in heterogeneous catalysis, that's actually rarely done. And the reason is you've got all these adsorbates on the surfaces, and we don't know the thermodynamics. And we just simply don't know the thermodynamics. And so there's a lot of estimation that's needed. There's a lot of fundamental science that's needed to either measure, which is difficult, or to predict by ab initio chemistry in some way. And I'll come back to these topics. Okay, let me shift now back to reforming. I showed a slide that had autothermal reforming, dry reforming, and so on in just as global reactions. So here's what a typical steam reformer looks like at the industrial scale. And I want to call your attention to the size of a person. These are large reactors, typically, and in ways that produce millions of tons of hydrogen annually for ammonia synthesis, for petroleum upgrading, and any number of things. So recall that the steam reforming is strongly endothermic, so we need to produce heat. And so in this reactor, refinery, we burn half of the methane simply to produce the heat. I mean, on all other things being equal, that's inefficient. We burn to make the heat, to make the products we need. So we ask then ourselves the question, can this be intensified in some way that makes that burning either more efficient or not burning per se, but deliver the exotherms differently? So that's the spirit in which I want to talk about process intensification. And in this talk, I'll talk to two broad ways to intensify. One is in microreactors. This, I'm holding a little ceramic reactor that I'll say in a few minutes more what the internal structure of that reactor looks like and how it performs. And the other is in membrane reactors, where again we're spending a lot of time mainly in ceramic ion transport membranes to intensify with membranes. So in this illustration, I'm doing basically a partial oxidation, but introducing the oxygen through an oxygen transport membrane right the way along the length of the reactor, rather than premixing at the front end. And I'll talk about why that's useful as we go on. Now, I showed a picture of a large refinery scale reformer where I had large flames that were producing the heat to support the reforming endotherm. Here's one concept for integrating in a microreactor, where microreactor means channels on the order of a millimeter or so, where now we run two channels. One is doing the endothermic reforming, the backing channel is running an exothermic oxidation process. So in principle, this works great. In practice, it works not quite so great because it's very difficult to get the endotherms where you need them, the exotherms where you need them, and do the balancing and so on. But in principle, it's a good idea to couple closely exothermic processes, endothermic processes, as opposed to simply making a flame. Okay, now, let me take a little bit of a short detour here. Here I've shown that the catalyst as a wash coat, much as would be in your catalytic converter in your automobile, but you see no detail to what that looks like. So one of the things we've done recently is to reconstruct the wash coats and look at a microscale of that wash coat structure. So this is a commercial partial oxidation catalyst that we acquired through the good graces of, again, Olaf Deutschmann in Karlsruhe. And this is a focused ion beam SEM, scanning electron microscopy slice of a little bit of this wash coat. But with the FibSim, we can now tomographically reconstruct the wash coat structure in whole. So here on the scale of a few tens of microns is what that tomographically reconstructed catalyst wash coat looks like. And if you follow this literature, we often look at wash coats as though they're collections of packed spheres or ordered holes, such as, and come up with Thiele modulus, this kind of a thing. But when you look at the actual microstructure, you would be hard-pressed to say that looks like a collection of packed spheres, right? It just doesn't. And so what we've done now with this is to go into these, let me call them cracks, these crevices that go into the wash coat structure, and now pull those out electronically, which we can do because we have digital representations of the microstructure. And from that, do three-dimensional simulations of the reaction to fusion trade-offs deep within these pores, or these crevices. And in this case, we've generalized that in terms of a Domkohler number, looking at reaction to fusion trade-offs. And as you would imagine, if the surface chemistry is slow compared to the diffusion, then you get deep penetration into the cracks and you pretty much use all your catalyst. If, on the other hand, the surface chemistry is fast, all the chemistry happens out near the surface, and the platinum or rhodium or whatever you put down here is actually not being used. So these kind of insights are quite important to how we optimize the wash coat structures in actual catalysts. Okay, let me now come back to the microchannels, where in this case I haven't shown the catalyst explicitly. But as you know, and actually you do know, there are many talks in this symposium this week about microchannel combustion, microchannel behaviors. Very high heat and mass transfer because of the small dimensions. Laminar flow, but very high heat and mass transfer because of the Nusselt and Sherwood numbers are constant. As the length scales decrease, you get very high heat and mass transfer. So that's a good thing. So this is a reactor, and I'll show some brief results. But we're making these from ceramics. Most of this technology is made from metals, which is a good thing. But we think we can get comparable performance, but much lower cost by ceramics. But that's a little bit of a different story. What I'm showing here is that we've had to do some things in the design of these reactors, and I'll call specific attention to these little pedestals that sit here, which fluid mechanically is actually quite a bad idea. I mean, you really wouldn't want to do that. But from a manufacturing point of view, we had to do it to get good lamination between layers and so on. So not only do we need to be concerned with trade-offs between the chemistry, the fluid mechanics, the heat transfer, and so on, we need also to be concerned with design decisions that lead to manufacturability. And so we spend a lot of effort in computational fluid mechanics dealing with heterogeneous catalysis, complexity in heterogeneous catalysis. I mean, certainly tens of reactions, typically not hundreds of reactions, fluid mechanics in the reactor bodies, and heat transfer. And so that's less computationally expensive than some of the DNS work that's done here, but it's still computationally very expensive. And so we've spent a lot of time, we continue to spend time trying to accelerate these three-dimensional simulations. And I call particular attention to some recent work where we've taken the ideas from Steve Pope on ISAT, in situ adaptive tabulation, and implemented that into heterogeneous catalysis with very great accelerations. Once we've built, well, certainly once we've built the tables, we can solve the reacting flow problem basically at the same cost as the non-reacting flow. I mean, very great accelerations. Here's just, I won't dwell on this, but here's just here's our reactor in a test stand. It's shown exposed here. Normally, of course, there would be insulation around it. And in this set of experiments, just looking at the methane conversion, hydrogen selectivity as a function of carbon-oxygen ratios, and so on. Again, I called out earlier on, we really care a lot about the carbon-oxygen ratios because we care about the chemical content of the syngas. Okay, let me now shift our attention to membranes. So up to now, I showed a couple of reactors, but with no membranes. They were intensified by virtue of small channels, microreactors, and so on. So look here at a typical steam reformer. Typically, we pre-mix the methane and steam beforehand. You produce a lot of hydrogen, but this reaction can equilibrate. I mean, all reactions equilibrate at some point. And so once we've equilibrated, you can get no more conversion. So if we can pull out the hydrogen through a membrane, then we can keep shifting this reaction to get further conversion of the methane. And so palladium alloys are good hydrogen transport membranes. We work mainly on ceramic ion transport membranes, mainly of the barium zirconate, barium cerate class. Here's basically the same configuration, catalyst in the interior body, but now let's look at a partial oxidation. So in this case, as again, I think most of you know, if we pre-mix the methane and oxygen, put it here, we'll get a very large exotherm right at the front end of the catalyst bed, and we'll produce a lot of total oxidation products, which will then downstream reform, which is inefficient if we can avoid it. So in this case, we're using oxygen ion transport membranes to introduce the oxygen just in time and thereby control the temperature. And I'll show other examples of that as we go on. Oh, so let me, yeah. So in essentially all partial oxidation processes, you really want pure oxygen. You really don't want to do a nitrogen separation later. So let me talk briefly about air separation, and that'll connect back into some of the membrane technology. So here are oxygen transport membranes made mainly of things like calcium-doped lanthanum ferrite. These have been developed, these particular ones have been developed by Air Products primarily for oxy-combustion applications. So when you look at this picture, unless you know what you're looking at, it just looks like a stack, like a loaf of bread. I mean, what is really going on? So in this image, I've split apart these blades, or these slices of bread, to look internally, and then done one more thing, which is to put a partial oxidation catalyst on the external surfaces of the blades. So in this case, this is again a design from Air Products, they feed air through this whole stack, goes through these small microchannels, separates the air, so it once separates the air and produces oxygen through an ion transport membrane to the partial oxidation catalyst. So again, intensified in the sense that microchannels, in situ air separation, combining unit processes. Here's another way this could be done. I mean, just laying out, and I should say, we're limited by our imagination in how to build these kind of reactors. So I'm showing some illustrations. They exist and are worth thinking about. Here's a design that Praxair has developed. So in this case, we're coming in with steam and methane, which are then fed to these endothermic reforming channels, which are filled with catalysts, and that's endothermic. But the reaction is only partially reformed. So what comes out of these yellow-brown channels still has some methane. It comes over here and feeds partial oxidation tubes, which are complicated in their own right. So there's an oxygen reduction catalyst here. There's a membrane, an oxygen transport membrane, and a partial oxidation catalyst. So that's exothermic, and those get red hot, and they radiate. And then air flows laterally across each of these blades, and there are many of those. So again, coupled the air separation process, a dry reforming, or steam reforming, and a partial oxidation in a way to produce syngas in a single reactor. All right, let me now turn our attention to what we can do with the syngas, and there are many things we can do with the syngas, but let's talk briefly about FischerTropsch synthesis, the objective of which is to take the syngas and produce a synthetic crude, which would then go to further downstream refining. So, as you probably know, most of the commercial FischerTropsch is practiced in very large reactors. I mean, 10-meter diameter reactors that are tens of meters high. Again, as a point of reference, showing a picture of a person. These are big reactors. And it's very difficult to control, to really control the temperature uniformity. In this technology, because the catalyst temperatures are low, 250, 300 C, what happens is you bring in pressurized water, typically around 20 bar, something like that, and boil it. But because you can control the pressure, you can control the temperature. And so you have very close coupling between the pressure, the operating temperature. But even so, these tubes are large, and so you have high temperature in the interior, low temperature on the exterior, and don't have as good a temperature uniformity as you would like. Slurry beds help that. Well, they help it a lot, but what I want to do now is call attention to what Velocys, a company called Velocys, is doing in their reformers and FischerTropsch reactors. So I'm showing here the core on a millimeter scale of a Velocys FischerTropsch reactor. What's going on is in these red arrows are now the pressurized water that are boiling to control the temperature. And these fin-like structures, so the catalyst is packed between these fin-like structures, which again is a very efficient heat transfer coupling between the coolant and the catalyst. Then we can take one of those cores and embed it into a meter scale reactor. So again, highly intensified. In this case, syngas comes in the top, comes down through the catalyst, coupled tightly to the cooling water, the pressurized water, which is cross-flow. Steam comes out the top, condensed water comes out the bottom, and FischerTropsch products come out the bottom. So again, going from a very large refinery scale reformer or FischerTropsch reactor to something that's kind of on the meter scale. Again, highly intensified. All right, let me again shift gears again to a slightly different topic, which is now, instead of going through reforming FischerTropsch, let's now try to do more direct conversion of the methane to other products. So I'll spend a few minutes talking about oxidative coupling of methane, actually a relatively old topic, but has still not achieved commercial success. So here in cartoon form illustrates the oxidative coupling process. We begin with methane and oxygen with great excesses of methane. In other words, we're really trying to do a dehydrogenation, not do an oxidation. But both on the catalyst surface and in the gas phase, the initial objective is to activate the methane to produce methyl. And then, as probably everybody in this room is well aware, if we've got lots of methyls, they can recombine to ethane and then subsequent dehydrogenation with the objective of producing ethylene, which of course is a very large commodity chemical with great value. So this process was first put forward in 1982, and with a lot of work up till now. A company called Soluria in the Bay Area, in California Bay Area, says that they either have commercialized or very close to commercializing this process. Anyway, I want to, with oxidative coupling in mind, now come back to the catalyst. So I showed a nickel reforming mechanism from Olaf Deutschmann, and we're actually, again, this community is reasonably comfortable with rhodium, platinum, nickel, but single metal catalysts. So those are very valuable and used quite widely, but not in processes such as this one. So in oxidative coupling, there are really two choices that are being pretty actively pursued. One is a sodium tungstate silica process, or a catalyst, where the silica is now in a cristobalite form, or a lanthanum oxide, which is typically doped with ceria or calcia. Just by looking at the pictures, it's obvious that these are more complicated catalysts than a 1,1,1 surface of rhodium or something like that. So in this literature, almost all the modeling literature uses a reaction mechanism coming from a group in Germany. But a thing to notice here is that despite the fact that these are complicated catalysts, the only species in this reaction mechanism are gas phase. In other words, in this reaction mechanism, there are no surface adsorbates. There's simply no surface adsorbate. It's all gas phase. So when you look at the rate expressions for these reactions, they don't look at all like mass action kinetics. They're very complicated empirical relationships that are developed to predict measurements, but are highly empirical. And so a thing that we're working on quite actively is to build the more elementary reaction mechanisms, which is a difficult task. I won't talk about that here, but I'll talk about similar activities in direct dehydrogenation chemistry. Yeah, so the oxidative coupling is exothermic, but if you let the exotherm run and go to high temperature, then you make too many total oxidation products, and it's an inefficient process. So we're quite concerned with controlling the temperature. So here's a reactor coming in with methane oxygen onto the catalyst bed. And by the way, this is work from Salim Senkin at UCLA. Some of the older among us may remember Salim Senkin was actually active in this community many years ago and then took a detour into catalysis and actually never came back. But anyway, what he measures with movable probes within this reactor bed is, first of all, a very strong exotherm within a few millimeters. So you put methane and oxygen onto this catalyst, it burns, for the lack of a better word. So you don't want that to happen. You really want the temperature to be low and thereby prefer the desired product, which is ethylene. So one of the things that Salim did is said, okay, well, why put all the oxygen in at the first place? Let's make a two-stage catalyst. We put some of the oxygen in at the outset, and then we inject some later. And what you get is two peaks, but less exotherm than if it was all mixed in the first place. Well, then it begs the question, well, how about 3, 5? How about making a membrane? Okay, so we'll go there in a minute. But with these kind of things in mind, here's a different kind of a reactor that has been put forward by the group of Guy Marin at the University of Ghent in Belgium, coupled with a German group in Berlin. Okay, so the wiring diagram here takes a minute to get your arms around, but let's break the catalyst into two reacting streams. So here's the oxidative coupling reactor, and a reactor that's, remember, exothermic. But we need to provide some way to cool that. We need to keep that cool, or the product streams to be cool. So let's run another process, which is a dry reformer, which is now endothermic. And in between these two processes, where the process streams never mix, we only exchange heat between the two process streams, we have a microchannel heat exchanger. So the gas comes out of this reactor a little bit hot, goes through this counterflow heat exchanger, and heats the reaction stream going into the dry reformer, which is now going to cool. And then do it again, and do it again. So what's the benefit of this? Well, instead of burning some fuel to produce the heat I need, such as I showed in this big reformer at the outset, here I produce the cooling and the heating from two product streams, both of which are giving me valuable products, as opposed to one just burning and I can't sell water and CO. Well, actually, I probably could sell some CO2, but basically you don't want to sell water and CO2. So can we combine processes, or yeah, that gives me two valuable product streams. Now, by many definitions of process intensification, you would say, well, wait a minute, that didn't combine unit processes. I actually made lots of unit processes. So on the face of it, you think, well, maybe that's not a good idea. I think it is a good idea. But then I think, well, do we have precedents for that, for expanding unit processes? And actually, in combustion, again, I expect to be quite familiar here, but in gas turbine, it's actually efficient to have intercooling between compressor stages and make up heat or reheat combustors between expansion stages. And the reason to do that, of course, is to turn what would initially be a Brayton cycle into an Ericsson cycle. And if I do this with many stages, we'll get a sawtooth behavior here that makes the compression and the expansion look more or less isothermal. So it's only an illustration to say that process intensification doesn't necessarily mean combining unit processes. There may be reasons to expand unit processes if we do it in an intelligent way. Let me give another example from, again, will be very familiar in combustion. So everybody's very, I mean, there's certainly not a single person in this room that's not quite familiar with opposed flow flames of various sorts. Here's just a cartoon image that shows, despite the fact that we have two-dimensional flow field, the temperature and composition fields are flat. And here I've taken a photo from Cal Shesadri's lab just to show that, in fact, that's what happens if you set it up correctly. Okay, so fine. Now, I've shown lots of examples of tubes with catalysts in the tubes and flow through the tubes. So what I'm showing here is a tubular flame coming from the group of Satoru Ishizuka in Hiroshima. And actually, this image was taken by Professor Balushi, who's also in this meeting today. So by analogy with the flatness of this flat flame, in the tubular flame, even though we have long axial tubes, the flame radius is independent of axial position. You know, if you set it up correctly, and that can be done. So it comes to my mind, can we use that concept to build a reactor? So here's a notional image, which has not been built, might work, might not work, but at least it's interesting, where instead of having flow along the catalyst bed, where I can have exotherms, endotherms, things change along the length of the bed, if I make a reactor like this, I can do a number of things at once. One is, let's put air in a central body, an oxygen transport membrane that delivers only oxygen, leaving the nitrogen here onto the catalyst bed, and then swirl in the methane on the outside. So if we could build this reactor, what we could say for sure, because we understand the mathematics of the similarity, is right the way along the length of this tube, everything will happen the same, independent of the axial position. That's a good thing. Now, we have to design it in such a way that the right thing happens independent of the length. But this is a very, very different concept that, as far as I know, nobody's even thinking about in the reactor engineering community, and might even work. Okay, let me close with a few comments about methane dehydroatomization. In this process, so in MDA, our objective is to directly dehydrogenate methane to produce benzene and hydrogen. And of course, we can easily write this reaction down and balance it and hope that it actually works. Now, the catalysis is now, again, complicated because every realization of MDA now operates on bifunctional catalysts. In this case, we activate the methane on a molybdenum carbide structure that's formed on the Bronsted acid site of a zeolite, a ZSM 522, something like that, where the atomization takes place. The problem is with, and I'll say more about this in just a minute, but even though I can write this reaction down, the thermodynamics actually doesn't want to do this. It wants to make benzene, but then it wants to continue molecular weight growth to naphthalene, anthracene, and so on, which is what we don't want. So we need a way to interrupt that. One of the ways to do that that's actually quite active in our group now is to use low levels of steam to preferentially attack the naphthalene, and we're doing that through mixed conductor membranes. Again, these are solid solutions of barium zirconates, barium cerates that have the property that they can move oxygen ions and protons. So we can move, by polarizing this membrane, we can move hydrogen in one direction and essentially move steam in the other direction. There's just a quick picture if you're not familiar with zeolites. Here's a picture of a ZSM-5, which one of the important things about the zeolites is the molecular atomic dimensions of these channels, which help with the selectivity just owing to size selectivity. Here I've just shown a methane molecule interior to one of these channels, but it's this Bronsted acid site where the cyclization chemistry proceeds. Okay, now how do we get a reaction mechanism? I said at the outset, the easiest thing to do is click on deutschmann.com, and then it just appears. But I just say that tongue-in-cheek. I mean, that works if you want to look at catalysis on rhodium or nickel or something like that. But if you want to look at a bifunctional molybdenum carbide zeolite, there's no place to click and get it. I mean, you have to figure it out. And so we're working hard on that. And when I say we, that means my colleague John Karakayas, who by the way was a student with Olaf, so that actually is connected to build these mechanisms. So the first place you start is with a mind's eye picture. And this mind's eye picture was published a couple of years ago by the group of Guy Morin I mentioned earlier from Ghent. And so they laid out it in a notional picture. We're going to activate the methane on the molybdenum carbide. We'll transfer some of the ethylene onto the zeolite, undergo a series of oligomerization reactions, protonation, deprotonation, ultimately cyclize into cyclohexane, protonation, deprotonation to make benzene. Now we want to stop here. I mean, we want benzene as a product, but the thermodynamics doesn't want to stop here. The thermodynamics wants to go on and make naphthalene and anthracene and higher aromatics. So that's a challenge. But in designing these reactors, we in order to bring the chemistry into the CFD, we need reaction mechanisms that can be understood by Chemkin or Cantera or something like that. I mean, I can't put this picture into a computer. So we've done that. I mean, it's an active work in progress, but this is what the reaction mechanism looks like more or less today. There's activation chemistry on the molybdenum carbide sites. There's atomization chemistry on the zeolite sites. Coming up with rate expressions is difficult. We've got to respect thermodynamics. We've got to be consistent with experiments, which we're doing. We're working a lot with the University of Oslo chemistry department who are doing experiments. So there's a lot of day-to-day iteration to come up with a reaction mechanism that represents what we can actually measure in the laboratory. Yeah, I alluded to this a few minutes ago. What happens through these membranes as you take more and more hydrogen off the catalyst, well, if you start with methane and remove all the hydrogen, that's obvious what you get. You get carbon, right? Right? I mean, that's obvious. But in fact, you don't go all the way to carbon typically. And as you remove more and more hydrogen, then the naphthalene yield competes with the desired benzene yield. We continue converting, but to the wrong products. So the thing that we're working on actually quite actively now is the chemistry, again, on these zeolite, these molybdenum carbonate zeolite catalysts, but the ability of a little bit of steam, not a lot, 1% steam, to preferentially attack the naphthalene and come back to ethylene and other smaller products. I mean, that concept in itself is not new in the chemical processing literature, but the ability to do this with catalysts, with membranes that can move protons and oxygen ions is in fact new. Okay, I want to, again, I close here with a few very quick comments about membranes, which I've mentioned in a number of contexts. So, again, I showed this image earlier, but in this case, I need a hydrogen transport membrane. Typically, that's a palladium or palladium alloy or a proton-conducting ceramic, usually a doped perovskite, barium cerate kind of material. For oxygen transport membranes, we've got more choices. Many of you who work on solid oxide fuel cells know very well that yttrium-doped zirconia is a good oxygen transport membrane. Doped ceria is as well. But those need to be polarized. In other words, you need electrodes to drive the ions. Other materials such as lanthanum strontium manganates or lanthanum ferrites can move the oxygen ions without polarization. There's lots of stability issues in both oxidizing and reducing environments. But in any case, we've got more choices on the oxygen membranes. So here's just a chart of some of the materials we're working with. Start here again, perovskite structure, lanthanum, calcium-doped lanthanum ferrite has 3 mobile defects, the oxygen ions or the vacancies in Kroger-Vink notation, but charge compensation coming from 2 small polarons, the reduced and the oxidized oxidation state of the iron. These are electrically conductive. So that means you can't put electrodes. You couldn't make a fuel cell out of this material because it'll just short. It has too much electronic conductivity. But it's a good oxygen transport membrane. Doped ceria has 2 mobile defects. One is the oxygen ion, and the other is a reduced ceria. It's not electronically conductive, so to move the ions, you have to polarize it. Also means you can make a fuel cell, and people do make fuel cells out of ceria electrolytes. Yttrium-stabilized zirconia, again, that's much more known in this community because of solid oxide fuel cell technology. Is essentially a pure oxygen ion conductor. In oxidative coupling, there's a fair bit of work using nanoporous alumina. Now, that's not perm selective, but if you can control partial pressures, these can be effective, and they're cheap, right? So there's trade-offs there. Palladium alloys are well known for hydrogen separations. They work well. They're expensive. They work well. This is the space that we're playing in actually very, very actively in developing these, again, perovskite, doped perovskite structures, which are mixed conductors, but now we have protons. Again, unless you're familiar with Kroger-Vink notation, this might not look like a proton to you, and this may not look like an oxygen ion, but that's what the nomenclature says. We think, it's a little bit controversial, but there's some discussion in the literature. We think that the charge compensation in these materials is by a small polaron that's associated with the with the oxygen anion in this lattice. Okay, let me summarize by saying things that might even be hackneyed in the sense that everybody's knowing about scale disparity, multi-scale modeling, these kind of things. But in the things I've talked about today, we need at least to understand from an insightful point of view is what do these catalysts really look like. I've talked about sodium tungstate-based catalysts. I've talked about nickel. I've talked about bifunctional molybdenum carbide zeolites, and they're all really quite different. But at least we need a mind's eye picture of what those catalysts look like at the atomic scale. And from that, we've got to build reaction mechanisms. Well, to do modeling, we need reaction mechanisms, but in technology, you need to bring this sort of insight into something that looks like pelletized or powders, but in any case, some way to realize the actual catalyst in a bed. It might be a wash coat, it might be a packed bed. And then, even that we understand this perfectly at the lab scale, where we've got experiments through flow tubes or what have you, that obviously needs to be upscaled into the core of some sort of a reactor. Here I've shown a little microreactor that along the lines of what Velocis does, but there are many realizations of that, and I think we're limited only by our imagination as to how to optimize such processes. And then at that scale, we've got to come to the actual scale of technology that can really deliver products. And certainly a partial list, but I think there are just so many places that this community can contribute, from materials, catalysts, how do you support, what are the best membranes, how do you interface membranes with catalysis. I mean, there's a lot of both scientific and technology questions there that are open. Theory, this community, broadly the combustion community, is actually very, very good, maybe leading the charge in ab initio chemistry for gas phase chemistry, probably less so for catalytic chemistry, but in some sense the tool sets are quite similar. Thermodynamics, I mentioned briefly, microscopic reversibility, trying to understand something about the thermodynamics of adsorbates and say on surfaces, and kinetics. I mean, it's a very, very big challenge because we keep changing catalysts all the time. And so, you spend years to build a reaction mechanism, and then somebody just changes the catalyst, and you start over. But in many cases, you're close to starting over. So it's challenging. Here again, where are places where this community is really way ahead of the world, which is in diagnostics, laser diagnostics, in the laboratory. But a very important topic that I haven't even mentioned in this talk is real-time control. I mean, these processes need to be controlled. So we work a lot on so-called model predictive control. Can we take physical understanding and then through state-space modeling embed that physical understanding in real time on microprocessors in the reactor control? But all control is feedback. So unless you're measuring something that's useful, you don't have any basis for the feedback. So can we turn diagnostics at the laboratory scale into sensors at the technology scale is actually a very important topic. And then building reactors, again, limited only by our imagination, but with concepts such as process intensification guiding us to make more and more efficient processes is our objective. Okay, I'll close with a few acknowledgments. Much of our work is supported by the Office of Naval Research with Michelle Anderson. Much of what I talked about today here was supported through a BRI, Basic Research Initiative from the Air Force. Qiping is probably here someplace, but Qiping, well known to the combustion group and is also quite interested in how can we take the foundational concepts of combustion and move them into other areas. A lot of our ceramic work is done with Coors Tech, where Grover Coors is actually a very close colleague and an excellent electrochemist and an industrialist. And many colleagues at the Colorado School of Mines, and in fact many colleagues worldwide. Okay, with that I'll close, and that's, believe it or not, actually on time. Okay.
Well, thank you very much for a very interesting and challenging talk. I believe as a community you need to expand your boundaries to prosper. And I think that Bob has done more than most of us in doing this. He has been developing models and software that has really expanded our possibilities of scientific research within combustion. But he's also expanding our boundaries in another way, as he has shown today also that he's expanding our notion or our understanding of what the combustion area is really about. And I think this is also very important. So we would like to thank Bob for an excellent plenary lecture. I don't think we have time, unfortunately, to questions, but
Okay, thank you, Peter. Thank you, Brian. Good. Oh. That's right, yeah. Okay, thank you. Okay, thank you.